lot of temperature measuring devices are there. We will be mainly focusing on three temperature measurement devices: thermocouple, RTD, thermistor. These three are very commonly used in measurement. So we will focus on these three. There are other measurement devices which are also used in measurement in our mechanical engineering applications. But, considering the scope of the subject, I think they are not included in the syllabus. However, I urge you to go through other sensors as well. There are pyrometers. There are other optical measurements that are available for measuring very high temperatures, widely used in industries like foundry and other places. You have non-contact type measurements. Even contact type other temperature sensors have not been discussed. Please go through that by yourself so that you will be able to understand when you get into the industry. So we will be discussing these three: thermocouple, RTD, and RTD means a resistant temperature device. We have thermistor. It's a resistor whose resistance changes with respect to temperature. Okay. All of you know what is temperature. What is temperature? Temperature is a measure of average kinetic energy of the molecules. If you have a medium, have a substance, there are molecules in it. Molecules are moving in random fashion. That means it has a velocity. If it has velocity, if it has mass, naturally it will have kinetic energy. Some may have high kinetic energy, some may have low kinetic energy. The measure of average kinetic energy of the molecules is temperature. So temperature and pressure has very close relation. As I told you, I have discussed this in other recorded video lectures. Go through that, that will be useful for understanding the fundamentals well. Due to time constraints, I am not going into the molecular explanation of what is temperature, how it is related to pressure for liquid, gas, and solids. I am not discussing it. Go through those. Now, these are some of the commonly used materials: nickel, copper, cobalt. All that are all mostly used for making the thermistors. Normally, basically it is a resistance value that we measure. Yesterday, we have learned how to measure change in resistance using a circuit. What is that circuit name? Huh? Huh? LED.
Wheatstone bridge.
Wheatstone bridge. Yeah. Wheatstone bridge is the simplest circuit. Simply 4 resistors are there, and one galvanometer and one power supply. That's all. Nothing more. So, Wheatstone bridge is the simplest circuit which is used for measuring change in resistance. It is not measuring the resistance, it is measuring change in resistance. Okay. Thermistor is also basically a device whose resistance changes with respect to temperature. So essentially, if you know how to measure change in resistance, that means you know instrumentation with respect to RTD as well as thermistor, because both RTD and thermistors change its resistance with respect to temperature. You see, negative temperature coefficient material, which are most of the thermistors are made of negative temperature coefficient. What is meant by negative temperature coefficient? When temperature increases, the resistance decreases. Okay, that's negative temperature. There are sensors with positive temperature coefficients that, as temperature increases, the resistance will increase. Whereas for thermistor, this is the case. And how this temperature and resistance are related, that's a big complex equation. Now you have Steinhart equations relating the temperature and resistance. Now you have the temperature in Kelvin, you have resistances in ohms. R is the resistance of that particular sensor at a given temperature. RF and TRF are at reference conditions. A1, B1, C1, D1 are all coefficients that you can determine in 2-3 ways. Okay. The simplest way is refer to the tables. You have tables like this given by manufacturers. A1, B1, C1. I don't know whether you will be able to read from the receipts, but it is a table. Simply look up that table for a given material, given temperature. Put that coefficients, you will be able to use it. Of course, it can be determined experimentally as well by measuring 3 different resistance values at 3 different temperature values you can do, and then do a matrix inversion you can do. You can also find out these values by using least square. They're all too much of detail, we are not going to. So, this is, let's say, this is the thermistor RT, this is the voltage source, simply a battery that's connected to one side and the other side. This circuit alone is actually a voltage divider circuit. You remember voltage divider circuits? You might have studied in basic electrical electronics. All of you have studied basic electrical and electronics course. You might have studied voltage divider. Voltage divider? No. Yes or no? Yes, but forgot. Okay. So this, whatever is the voltage, let us say this is 10 volts. This is 1 ohm, this is also 1 ohm, for example. So, if you put equal resistances, the total voltage will be divided into 2 halves. Okay. So, you have a 10 volts battery you connect, 1 ohm, 1 ohm, or 1 kilo ohm, 1 kilo ohm, same resistance you put. Here you will have 5 volts, here you will have 5 volts. If you take connection here, with respect to here you will have 5 volts, with respect to ground you will have 5 volts. So, you will have 10 volts. Suppose you put unequal resistances, what will be the voltage that I will get here? What will be the voltage I get here? Sum of these two voltages will be 10 volts, there is no doubt about it. But how much I will get as V out is given by this formula. This RT means the thermistor resistance value. Normally in a voltage divider circuit we will represent this by R1, this by R2, and this is Vs. So we will say Vs into that. If suppose you want voltage across this resistance, you will say R2 divided by R1 plus R2. Here it is RT, so it is RT divided by RT plus R1. Okay, that's the formula to find out what is the voltage across this resistance RT. So this V out is Vs, a fraction of that Vs. Okay, so let us say if this is 3 volts, this will be 7 volts. Remaining 7 volts will be. This is a voltage divider circuit. We are not learning voltage divider circuit, that you should know. Voltage divider circuit you can use and measure the voltage across this. You will get some voltage and then calibrate this voltage in terms of actual temperature. In terms of actual temperature. I always say that measuring displacement, velocity, or vibration, upon calibration you will be able to directly calibrate. After Cat 1, we are going to learn the calibration circuit. Suppose you have some 3 volts here. Okay. The temperature now is some 37 degrees Celsius. 37 degrees Celsius. For that, you get some voltage here. Some voltage. 3 volts, 3.5 volt, 3.2 volt, some volt. How to convert this 3.2 volt to that 37 degrees Celsius? If it is 40 degrees Celsius, you will get corresponding some voltage. We don't want to read that voltage. We want to read, if 40 degrees Celsius is actual temperature, we want 40 in the display unit. So that we can note down it is in the degrees Celsius, so 40 degrees Celsius. So how to convert these voltages, which are small in number, but proportional to the temperature value, how to convert that value electronically into the actual parameter is the subject matter that we will be learning in detail after Cat 1. In fact, your open book tests are all based on this particular subject content. Okay. So for now, you say you just accept, yeah, yes sir. Upon calibration, you will be able to. So you have some amplification, some scaling circuit. After that, you will be able to read the temperature directly from the display. This is the recent development of integrated silicon linear sensors. These are all 3-leg sensors. The advantage of these devices are the linearization, the so-called signal processing, a bit of pre-amplification, all that, even filtering to some extent, is done inside the sensor itself. So whatever you get, Vitalik, sorry, you please come next class. What is it? Is coming one day late is alright. Coming every day late is not acceptable. Please join me next class. So you have three-legged electronic component. It's basically a semiconductor component, and one is power supply, other one is ground. In the V out, you will get the voltage proportional to the temperature. Simply, you can directly connect it to any data processing card and then adhere it without any signal processing. Whereas here, you need to do a lot of signal processing to get to know what is the actual temperature. Here it is straightforward. Because today IC technology has developed to a large extent. People have put all linearization and signal conditioning circuits inside this itself. All small chip. It will be less than my little finger size. The size of that this is smaller than my little finger. So with that, all circuits are inbuilt because of the IC technology to measure the temperature. Cost is also very less. Less than 100 rupees, you will get such sensors. Next class we will see. Thank you for your understanding. I say thank you for your understanding. Next class. This is the summary of the characteristics. Now we have different characteristics and the corresponding parameters I have given. Nothing to explain, but for you to go through the parameters of this particular sensor. Okay, that is the thermistor. Okay, and the thermocouple is a big topic. It's a big topic. Now, 2-3 hours we can speak on thermocouple alone. Okay, but in let's say 15 minutes we have to discuss. We have to condense all that to 15 minutes. So, what is that you should know in thermocouple? The basic principle. Thermocouple is actually a two-terminal element consisting of two visible elements. Okay. The first thing that you should know about thermocouple. Couple means two. Thermo means something related to temperature or heat, isn't it? So the couple means two. Normally a boy and boy, we will not call it as couple, at least in Indian culture. Okay. Couple means one boy, one girl. Okay. So it's a dissimilar item joining together, call it as couple. Okay. So here the material has to be dissimilar. The same material does not form the thermocouple. Okay. So you have to have two different materials joined together at one end. You call that as thermocouple. The simplest sensor in any parameter is thermocouple, because all you need is two wires. One made up of, let's say, copper, other made up of, let's say, some tungsten or some other material. Simply you braze it or weld it or solder it in one end, thermocouple is ready. Thermocouple is ready. You can start measuring temperature with respect to that. Of course, a bit of calibration is needed. Some pair will have better sensitivity to temperature. Other pairs will have little less sensitivity. So people have experimented and found some combination of materials, the two different materials, which are very good response towards the temperature, and that they have placed it in the market. That I will show you some of the common. Okay. I think I have deleted that slide. Many unwanted slides I have deleted as part of that. I have deleted. The commonly used materials, pairs, K type, J type, S type, E type. There are different types of thermocouples available. It will have particular material combination. One wire is made up of copper, other wire is made up of Constantine. You call it as some type. That will have particular characteristics that can be used for a particular range of temperature. Okay. So thermistors and RTD, resistance temperature device. RTD both works on the resistance principle. One is having negative temperature coefficient, that is thermistor. RTD will have positive temperature difference. So if you have a device, you don't know whether it is RTD or thermistor, one easy check that you can do is simply take a matchstick, slightly heat it, and closer to the flame, don't burn it, but closer to the flame you take it, measure the resistance value. As temperature increases, if resistance value increases, then it is RTD. If the resistance value decreases, then it is thermistor. So you can easily find out whether. Otherwise, change in resistance proportional to the temperature. By measuring change in resistance using Wheatstone bridge, you measure the temperature. So RTD and thermistor both are working principles. Now thermocouple. The rest of the class is only for thermocouple. Okay. Here you have dissimilar material and joined together to form a thermocouple as discussed here. And we use two effects. One is Seebeck effect, other one is Thomson's effect. What is Seebeck's effect? Seebeck effect. You simply heat a conductor. You will see that the voltage is set up to the cable, in the wire. Simply heat a material. An EMF is induced in very less. Voltage means it's not a big voltage that you can use. Very less, maybe millivolts or microvolts. The voltage will be developed inside the voltage. But to measure that voltage, you cannot use the same type of material. You have to use another type of material. Okay. Then only you will be able to sustain the current that is there inside the circuit. And that is found by Seebeck, so it's called Seebeck's effect. It's called Seebeck's effect. So he says, if you have nickel chromium alloy, here also nickel chromium alloy, you will not be able to sustain the current and you will not be able to measure even what is the voltage that is developed. But if you have a different material here, let's say here it is nickel chromium, here it is nickel copper, then when you heat one end, heating is important. Without heating, the EMF doesn't come. You have two different material. So this is a junction. That's called hot junction or measuring junction. People call that junction. You heat it. That's why we put a candle there and then showing the heating action. You heat it. A thermoelectric EMF is set up. A thermoelectric EMF, and thermo current is flowing through that circuit. You connect this to a galvanometer or an ammeter, you can see a small amount of current is flowing in the circuit. There is no battery, there is nothing. All you have is two different wires connected to a galvanometer or any current measuring device. One end you heat, other end is kept at room temperature. Okay, let's say room temperature. Both ends should be at the same temperature. See, this is one junction. Suppose if you connect these two, this is another junction. Okay, so both are not same junction. There are two different junctions. So this is called a hot junction or measuring junction. This is cold junction. This is called cold junction. That has to be necessarily kept at different temperature than this. That both should be at the same temperature. That should not be at two different temperatures. So these are all mandate things for measuring the thermocouple. Now the thermoelectric voltage or thermoelectric EMF. EMF and voltage are more or less same. Okay? So we use synonymously. So thermoelectric EMF that is generated is proportional to the amount of temperature, amount of temperature difference between the cold junction and the hot junction. The temperature difference between hot junction and cold junction is delta T. Proportional to that, the voltage is generated. That's thermoelectric voltage. Up to this is clear. Thermocouple and thermocouple, hot junction, cold junction, Seebeck effect, Thomson's effect. Seebeck effect. Suppose I want to measure the temperature now. This is two different material. I simply roll it together, make a junction. I heat it. This side I connect it to thermocouple. it's very difficult to measure the temperature. It's very difficult to measure the temperature. The blue color line, I hope you will be able to distinguish the color. The blue color line is one material. Red color line is another material. The colors represent the type of material. I connected like this. Now, I want to know what is the voltage, I want to relate that to the temperature. It's very difficult. Unless we keep the gold junction at same temperature and known reference value, it is not possible to measure the temperature, actual value of temperature at hot junction. So, because the voltage developed is always delta T. Delta T means you should know what is the temperature here, you should know what is the temperature here. The temperature difference between this delta T, proportional to that delta T, there is a thermoelectric EMF and thermoelectric current that is being generated in the circuit. If you don't know what is the temperature here, you will not be able to quantify what is the temperature there. Okay? Because V is directly proportional to delta T. Delta T means T2 minus T1, for example. If you want to know T2, you should know T1. Then only you will be able to find out V. V is T2 minus T1. T1 you should know, so that T2 you will be able to. T representing temperature. Now, to determine the absolute temperature at hot junction, this is what I am talking about, hot junction. You need to know the temperature at the reference junction. You should know the temperature. Already we don't know the temperature, that is why we are using thermocouple to measure the temperature. In order to use thermocouple, you should know the temperature of the gold junction, means it doesn't solve the problem, it creates another problem. Okay. So generally what people will do is, they put these two wires into a known temperature of an ice bath. What is the temperature of an ice bath? 0 degrees Celsius. So now they put those two wires in ice bath. This junction, this hot junction, you connect it to the material whose temperature we are interested in. So this we know it is in 0 degrees Celsius. Now whatever is the temperature, that difference is, now this is 115 degrees Celsius, this is 0 degrees Celsius. Now what is the temperature difference? 115 degrees Celsius, isn't it? Right? So now proportional to 150 degrees Celsius, you will find some voltage. That voltage you take, calibrate it, you will be able to measure it. Is this clear? Right? Does it make sense? No. Wires? This is thermocouple part. Up to thermocouple part, this should be same wire. This is one material, let's say it is iron. The blue color line is another material, let us say it is constantine. That is J-type thermocouple basically. Yeah, I have mentioned here. This is the J-type thermocouple that we have. And up to this, it is two different wires. After this, this can be a copper wire. Normally when we use for measuring. As long as you bring these junctions in compensation, same temperature, even this iron and copper is also dissimilar. That will not create any problem. There are 5-6 thermocouple laws that we are not covering. Go through it. That laws will describe, even though if these two are two different material, that will not create any additional EMF in the circuit, because these two pairs are all in the same temperature. So the third introduction of the third element, let us say this is copper wire, will not add additional EMF in the circuit because of this similarity. Because temperature is maintained constant. Both junctions is maintained at the same temperature, so it will not produce any thermo EMF. Even though, see, to produce thermo EMF there are two conditions. One, material to be dissimilar. Two, temperature should be different. You form two junctions. With respect to one junction, other junction should be at different temperature. If this is established, however small, there will be thermoelectric EMF. This is principle. But if dissimilar material you are not able to maintain, or if different temperature if you are not able to maintain, thermoelectric EMF will not be there.
Why do we need to have different?
Different?
Why do we need to have different
Yeah, copper, it's cost consideration only. Constant time is costly compared to copper.
So, sir, we could have used copper only, like,
Yeah, very good question. The pair that we found for the thermocouple, let's say iron is very cheap, aluminum is very cheap, copper is also relatively cheap compared to other materials that we use, nickel, chromium, palladium, constantine. Compared to that, copper is cheap. So copper itself we can use, copper, iron, like that. The amount of voltage that we get for the temperature difference is very very less. We want for a pair of material, if let us say cold junction is 0, ice bath only always, hot temperature is let's say 150 degree or 200 degrees Celsius, 200 degrees Celsius, 0. So totally temperature difference is 200 degrees Celsius. If I use copper and iron, I am getting 0.1 millivolt proportional to that some voltage. Suppose I use iron and constantine, I am using 5 millivolts, 6 millivolts. Which one you will prefer? Even if it is little extra cost I have to pay, I want more and more signal so that I know whether it is noise or signal. While measuring, you will always get some reading. If you build the sensor by yourself or while measuring, you will know. Some reading will come. Even if you keep a multimeter or oscilloscope, some waveform will come, some reading will come. You don't know whether it is the intended value or it is because of some noise that is picked up. Okay? You don't need to even measure. You take a thermocouple, simply you keep it near the switch box. Inside the switch box, 230 volt, 55 amps current is flowing. So you simply you keep near to that one thermocouple, connect it to an oscilloscope, and then see this small noise component will come. And if you enlarge it, it will be a 50 hertz signal that's there inside the AC line that it get interfere with the voltage developed in the thermocouple and it will come. You will be able to see. So you wanted to know whether it is actually a noise or it is the signal that is coming from the thermocouple. So the higher and higher the voltage that we get as an output from the sensor, it is easy for us to distinguish between noise and a signal. If voltage itself is very less, noise is also normally magnitude small. We don't know whether it is noise or signal. So we always, at any cost, would like to increase the output voltage of the sensor so that we get a better, or not better. It's easy for us to do signal processing, and then we get some information out of the signal. If you use same copper, or copper and low cost material, the amplitude of voltage that we get because of the temperature differences is very low. Sorry. So this is the iceberg method for doing temperature compensation. So keep these two in ice bath so that both these junctions are at the same temperature. And the third material, copper wire, normally used for measuring the voltage. Probe from a multimeter, something like that. Or a track in the circuit is made up of copper wire that will connect it and measure. So this is how you measure temperature using a thermocouple. Okay. Look at the nonlinear Seebeck coefficients. This is actually Seebeck coefficient. That's look at the range of thermocouple that's used. Goes up to 1000 degrees Celsius, 1500 degrees Celsius also. If it is R type and S type thermocouples can be used for very high temperature range. Whereas the T type, J type also goes up to some 750 degrees Celsius or something like that, starting from 0. Okay, there is some non-linearity, and you see except R and S, you see the non-linearity, even the coefficients are very high. Okay, so a lot of computational work needs to be done in order to convert this non-linear relationship of Seebeck coefficient that also affects the voltage that is produced. So it's not perfectly linear. The voltage that is produced is not perfectly linear to the temperature difference. There is a non-linearity in it. In a particular range, that non-linearity will be minimal. Either we use only in that particular range, that small non-linearity we will ignore. That's one way of using the thermocouple. Or we should have good computational resource inside, compensate for that non-linearity and get a linearized output if you are using for the entire range. Yeah, this is what I was referring to. I was searching for this one. See, this is nickel chromium if I use as a thermocouple material. This is called E-type thermocouple, and that cost is different from iron versus constant iron. This is nickel versus nickel. This is nickel chromium versus nickel. This is platinum rhodium versus platinum. Platinum rhodium versus platinum. Of course, different compositions, and copper versus constant iron. For all that, you can see what is the. Of course, here they have given the coefficients. There are graphs available. You will be able to see for this graph. This is the voltage output that you will get for this much temperature difference curves. So from there, you will understand copper and iron has very low voltage compared to these combinations. These combinations are standard combinations which people have found to give high voltage output for the given temperature. That's why they have been given some technical commercial name, S type, R type. You go to the shop and ask, sir, you give me nickel, chromium, nickel thermocouple, that fellow will not understand. You simply say, give me K type thermocouple, he understands. So that's a commercial name. K type, S type, R type. They simply gave a commercial name for that. But it's a trade name. So people will understand and then maybe. And these are all the coefficients table. I just put it in the slide so that you will be able to understand. Sir, anytime I want to measure temperature using thermocouple, do I have to always carry an ice bag with me? No need. You can keep it at the room temperature, but we should know what is the room temperature. It is to be at the known temperature, that's all. Why we keep in ice bag? Because we know ice bag temperature is 0 degrees Celsius. It can be kept at room temperature as well. One hot junction is in the place where temperature is to be measured. The cold junction can be somewhere hot junction can be at the temperature at which it is measured. Cold junction can be in the room temperature, but we should know what is the room temperature. Because from morning till night, the room temperature keeps varying. At least there should be 4 to 5 degree variation. Okay. So we should know what is the temperature. So for that, what you can do, this is hot junction. These two combinedly form cold junction, but we should know what is the temperature. For that, what do we do? We put one thermistor there and then find what is the. We have a thermocouple measuring setup in our lab. We don't use ice bath. You can go and see. Then what do? We use another sensor, typically a thermistor. Thermistor you can get it for 60 rupees, 50 rupees you will get. Of course, then the corresponding signal processing also you can do it in 100 rupees. So 3-4 resistors and some voltage that you get it from the other supply. Less than 100 rupees you will be able to do entire temperature measurement using thermistor. So put a thermistor here, find out what is the cold junction temperature. Hot junction temperature anyway, that unknown temperature that will come. With respect to that, you will be able to calibrate what is the temperature. You can ask me one question, sir, we wanted to measure temperature. That is why we use thermocouple. Why you use another temperature measuring device, RTD, to measure some cold junction, so-called cold junction? Directly you use RTD and measure the temperature. Why all this problem? RTD can measure only from, let's say, some 0 degrees Celsius, or not even 0 degrees, some 20-30 degrees Celsius, to some 300 to 450 degrees Celsius, not more than that. That is the range of temperature that for most commonly available thermistor material, RTD material, that is the temperature you can measure. Thermocouple can measure up to 1000-1500 degrees Celsius. When you want to measure higher temperatures, you have to depend on thermocouple. So you don't mind spending little extra money and measuring cold junction, so that I don't have to carry the ice bag along with me, but still I will be able to measure. So I know what is cold junction temperature. I know what is the voltage that is developed. I can find out what is the hot junction temperature. This is the actual circuit diagram of thermocouple signal processing. Okay. We will learn this after CAT 1. Don't get frightened by this. All simple stuff only, but looks a little complicated. This is an instrumentation amplifier, basically an amplifier. This is a low pass filter. All high frequency signals will be grounded, only low frequency signals will be sent off. And this is thermocouple, pole junction compensation. This is RTD, and all this difference is taken, and finally real signal. You will understand. Before end of the course, you will be able to understand this. Right. RTD we already talked about it. RTD looks like this. There are two connectors and a core, and there is a resistance wire in between. And the resistance wire here, the main difference between thermistor and RTD here, resistive temperature device or resistive temperature detector. Okay. So this measures the temperature with respect to resistance. The main difference here is the positive temperature coefficient. Okay, there in thermistor it is negative temperature coefficient. Here it is positive temperature coefficient. Both are cheap. This is highly linear, very stable. Even thermistor is stable. There's no big difference between all of them. So material, some behave positively with respect to temperature. Resistance and temperature characteristics are directly proportional. Other one is inversely proportional. Other than that, this is made up of some material, that is made up of some material. More or less, it all look same. Externally, in fact, I used to have this difficulty in the lab. We have both RTD and thermistor. We get mixed up. We don't know which is RTD, which is thermistor. So we use a multimeter and take a matchbox, that technique, and then we find out. So more or less, it's all same. Up to 0.01 degrees Celsius, we'll be able to measure. They say it is a little expensive. It's not very expensive. It's all cheap. Maybe because of the material cost, it may be slightly high, but RTD is also comparatively cheap, not very much. These are all the typical characteristics of thermocouple, RTD, thermistor, and integrated circuit. A comparison that you can simply go through it. Response time is very less in thermocouple, because that's very important in temperature measurement. You cannot take 15 seconds, 30 seconds, 45 seconds to show actual temperature, like thermometer. Thermometer is not suitable for temperature measurement for many applications because of its settling time. It takes more time to settle to one temperature and show you the actual temperature. Okay. So here in 1 second, less than 1 second, thermocouple will be able to show you the actual second. Whereas integrated silicon, that's very cheap. But of course, the disadvantage is it takes up to 1 minute to show you the actual temperature. Very, very cheap. But it takes little extra time. That's why for industrial applications, sometimes you will think twice before using integrated silicon. In the roadside, sometimes you will get digital thermometers, which is sold less than 100 rupees. Have you seen digital thermometers? For kids in the home, they wanted to check themselves what is the temperature, whether fever is there or not. People have some digital thermometer. That is made up of this particular sensor only. But normally it takes about 1 minute. You have to keep it so that no actual temperature is shown. You insert it immediately, whether you get the temperature or not. So time duration is a little high. Whereas thermistor is better. RTD takes a little more extra time. Thermocouple is the best. Range of measurement is also very high for thermocouple. You see, minus 270 degrees Celsius to 1800 degrees Celsius, we have some or other thermocouple for measurement. You will be able to find. It's not that one type of thermocouple will be able to measure from 270 minus 270 to plus 1800 degrees Celsius. Thermocouples are available. You can find some suitable combination to measure those temperatures. Similarly, RTD up to 900 degrees Celsius and thermistor up to 450 degrees Celsius, and the integrated silicon is actually the IC technology that we use. That's for minus 50 to 150 degrees Celsius. Small range. That's why these are all used in the toys. Many times it is useful. We just want to know what is the approximate temperature there. in many machines, we want to know whether the temperature is going much beyond the room temperature. It's a small indication. We are not interested in exact temperature value. A crude value, whether it exceeds the threshold limit, very useful because at cheaper rate, directly you can integrate it into the what is that? Analog to digital converter. DAC systems you can directly connect. Whereas thermocouple, if you have to connect it to computer, you need a lot more complicated data acquisition system. Whereas connecting this integrated silicon is much more easy. Signal processing is very less. Accuracy wise, which one is better? Plus or minus 0.5, 0.01, 0.1, 1. Which one is better?
Thermistor.
Accuracy wise. Which one is better? RTD. RTD is better. 0.01 degree Celsius you will be able to. Of course, linearity will go along with it. Ruggedness, of course, most of them are rugged only because most of the sensors will come with a metallic protection, metallic casing. So all are mechanically stable and rugged, fragility in that. And response time we already discussed. Excitation for thermocouple, excitation is not required. Why excitation is not required, only for thermocouple? Why excitation is not required for thermocouple? Bit louder.
So because it depends on the temperature differences, and already there will be a temperature difference here. So obviously the electrons will go and activity produce.
No, here you need to supply some current. Current source is needed for RTD. Here some voltage source is needed for thermistor. Whereas for thermocouple we don't need any battery or anything.
So it generates voltage.
Huh?
It generates
It
voltage.
generates voltage by itself. It's an active sensor. That's what you are planning to say, but I wanted you to explicitly spell it out. You have temperature difference. Proportional to temperature difference, the voltage is developed inside the circuit automatically. The sensor produces voltage, so you don't need to supply the voltage there. Whereas in case of RTD and thermistor, it doesn't produce any voltage or current. It simply changes its resistance. If you want to measure the resistance, you have to supply the current and check what is the voltage, change in the voltage, change in the current to measure the change in the resistance. So those things you should know so that you will be able to differentiate between these three.